Have you ever stood outside on a clear night, looking up at the stars, and felt that strange tug in your chest, the one that makes you wonder just how far it all goes? The universe stretches out in every direction, a vast ocean of darkness dotted with pinpricks of light, and yet it feels like there has to be an edge somewhere, doesn't it? Or does it? This is one of the oldest questions humanity has ever asked. Is the universe infinite, or is it just so enormous that our minds can't even begin to grasp its true scale? And here's the wild part: science still doesn't have a definitive answer. But what we do have are some of the most mind-bending theories and discoveries ever conceived, clues hidden in the fabric of space itself that might finally unravel this cosmic mystery. Think about it: every galaxy, every star, every atom in your body was once packed into a single, unimaginably dense point at the beginning of everything. The Big Bang set it all in motion, sending the universe expanding outward in a fiery burst of creation. But here's where things get truly bizarre. If the universe is expanding, what's it expanding into? Is there something beyond it, or does beyond even make sense if space itself is infinite? Some scientists argue that the cosmos goes on forever, an endless expanse where the same patterns of galaxies repeat over and over. Others say no, it's just so colossally big that it feels infinite, like an ant trying to cross an ocean. And that's exactly what we're diving into today. We'll explore the cutting-edge research, the paradoxes that keep physicists up at night, and the strange clues hidden in the afterglow of the Big Bang itself. From the mind-boggling concept of a multiverse to the eerie silence of the cosmic horizon, we're about to journey to the very edges of reality. So buckle up, because by the end of this, you might never look at the night sky the same way again. Right now, in this very moment, we're surrounded by the observable universe, a bubble of space stretching 93 billion light-years from one side to the other. That number alone is staggering, but here's the catch: it's not the actual size of the universe. It's just how much we can see, a snapshot limited by the speed of light and the age of the cosmos. Think of it like standing in a dense fog. No matter how far you peer ahead, visibility cuts off at a certain point. For us, that cutoff is the cosmic horizon, the farthest light that's had enough time to travel across space since the Big Bang. But here's where it gets even stranger. The universe is expanding faster than light can traverse it, meaning there are regions so distant their light will never reach us. It's not just that we can't see those places yet. They're forever beyond our cosmic sightline, like islands drifting away on an invisible current. And that leaves us with a humbling truth: the observable universe might just be a tiny speck in something vastly larger. So what's really out there? If we could somehow step outside our 93 billion light-year bubble, would we find more galaxies, more stars, more planets repeating endlessly? Or would the fabric of space curve back on itself like the surface of a balloon, making the universe finite but boundless, the wildest part we don't know? Because no matter how powerful our telescopes become, the ultimate size of the universe might always stay just out of reach. Let's rewind the clock way back to the very beginning. The Big Bang wasn't an explosion in space, it was the birth of space, time, and everything we know. In a fraction of a second, the universe went from smaller than an atom to something far vaster than we can comprehend, stretching and cooling in a process called cosmic inflation. And here's what's truly staggering. If inflation happened the way physicists suspect, the universe could be at least 10 to the 23 times larger than what we can observe. Wrap your head around that for a second. Our entire observable cosmos, those 93 billion light-years, might be a single grain of sand on an endless beach. Now, how do we even begin to guess the universe's true size? One of the biggest clues comes from something called redshift. When astronomers peer at distant galaxies, they notice their light isn't just dim, it's stretched, like the sound of a passing ambulance siren dropping in pitch. That shift toward redder wavelengths tells us those galaxies are racing away from us, carried by the expansion of space itself. In the 1920s, Edwin Hubble spotted this pattern and realized something revolutionary. The farther away a galaxy is, the faster it's moving. That's Hubble's law in action, and it's proof the universe isn't static, it's growing, stretching the very fabric of reality. But here's where things get even wilder. Cosmic inflation suggests that in the first sliver of a second after the Big Bang, space didn't just expand, it ballooned faster than the speed of light, smoothing out the universe like dough stretching in an oven. If that's true, then what we call the universe might just be a tiny bubble in an unfathomably larger multiverse, where other bubbles with entirely different laws of physics could exist. And yet, even with all this evidence, we're left with a haunting question. If space inflated so rapidly, why does the universe look almost perfectly uniform in every direction? That's the puzzle of the cosmic microwave background, the afterglow of the Big Bang itself, a snapshot of the infant universe, whispering secrets about its true scale. So where does that leave us, staring at the stars, armed with equations and telescopes, trying to measure the immeasurable? The universe might be infinite, or it might just be so vast that its edges are forever out of reach. But one thing's certain, every answer we find only deepens the mystery. So if the universe isn't infinite, what shape could it take? Picture this: you're an ant crawling across the surface of a balloon. No matter how far you walk, you'll never hit a hard edge, just an endless, looping path. That's the essence of a finite but unbounded universe. Space could curve back on itself, not because it's expanding into something, but because its very geometry creates a closed system. Albert Einstein's general theory of relativity gave us the math to explore this mind-bending idea, showing how the fabric of reality might bend in ways that defy everyday intuition. But how do we test something so abstract? It all comes down to geometry. Imagine drawing a giant triangle across the cosmos. In a flat universe, the simplest scenario, the angles of that triangle would add up to 180 degrees, just like in high school textbooks. But if space is spherical, like the surface of a planet, those angles would bulge outward, totaling more than 180 degrees. And in a hyperbolic universe where space curves inward like a saddle, they'd shrink to less. Astronomers have spent decades searching for these cosmic fingerprints, measuring the subtle warping of light from the earliest moments of the universe. The cosmic microwave background, that faint glow from the Big Bang, holds tantalizing clues. If space were curved, we'd see telltale distortions in this ancient light, like funhouse mirrors stretching its patterns. Yet so far, the data points to a universe so flat it's almost eerie. Does that mean space truly goes on forever? Not necessarily. Even a balloon's surface can appear flat if you zoom in enough, and the universe might be so vast that its curvature is simply too faint for us to detect. Here's the kicker: even if the universe is finite, it could still be so mind-numbingly large that crossing it would take longer than the cosmos has left to exist. Stars would burn out, galaxies would fade, and space itself would keep stretching until every last photon was stretched into oblivion. So whether it's infinite or just unimaginably vast, one thing's clear: the universe is playing by rules that push the limits of human comprehension. And that's what makes this mystery so intoxicating. We're not just measuring space, we're decoding the very blueprint of reality. The shape of the universe isn't just some abstract idea, it's the key to unlocking whether we live in an infinite cosmos or one with edges. And the craziest part, the answer might be hiding in the faint glow of the cosmic microwave background, the oldest light in existence. Scientists have narrowed it down to 3 possible geometries: flat, open, or closed. Picture a flat universe like an endless sheet of paper, stretching forever in every direction with no curvature. In this scenario, parallel lines would never meet, and the angles of a cosmic triangle would add up to exactly 180 degrees, just like the geometry you learned in school. Current measurements from the CMB overwhelmingly support this idea, showing a universe so precisely flat it's almost unnerving. But here's the twist: a flat universe doesn't necessarily mean infinite. Imagine a video game where you walk off one edge of the screen only to reappear on the opposite side. The universe could be structured the same way, finite in size but without boundaries, like a looped ribbon. That's the paradox of flat geometry. It could go on forever, or it could fold back on itself in ways we can't yet detect. The difference comes down to something called topology, the hidden wrinkles in space's fabric that might only reveal themselves at scales far beyond our observational reach. Now let's talk about the other possibilities. An open universe curves outward like a saddle, where parallel lines diverge and the angles of a triangle add up to less than 180 degrees. In this scenario, space would stretch infinitely, expanding faster and faster until everything is torn apart in a distant future called the Big Rip. Meanwhile, a closed universe would curve inward like a sphere, where parallel lines eventually cross and the angles of a triangle exceed 180 degrees. If that were true, the cosmos might eventually stop expanding and collapse back in on itself, a big crunch mirroring the Big Bang. So why does the evidence point so strongly to flatness? The cosmic microwave background is like a fossilized imprint of the infant universe, and its patterns hold subtle hints about the geometry of space. Tiny temperature fluctuations in this ancient light serve as cosmic measuring tapes, revealing how much or how little the universe curves. And so far, those measurements line up perfectly with flatness. But here's the catch: our instruments might not be sensitive enough to detect extremely slight curvature, just like you wouldn't notice the Earth's roundness standing in a small field. That leaves us with a humbling reality. Even if the universe isn't perfectly flat, its curvature could be so minimal that it appears infinite to us, a cosmic illusion on the grandest scale. Whether we're living in an endless expanse or a colossal but finite loop, one thing's certain: the universe's true shape remains one of its most tantalizing mysteries, teasing us with answers just out of reach. To grasp the true enormity of the cosmos, we need to talk about inflation, not the economic kind, but the universe's explosive growth spurt in its first sliver of existence. Picture a balloon inflating faster than the speed of light, stretching space so rapidly that quantum fluctuations, tiny wrinkles in the fabric of reality, got blown up to cosmic proportions. These ripples became the seeds for galaxies, and here's the kicker: if inflation happened the way physicists think, it didn't just happen here. It could still be happening out there, far beyond the edges of our observable universe. This is the wild idea behind eternal inflation. Imagine a vast, bubbling ocean where new universes constantly sprout like foam, each with its own laws of physics. Our entire cosmos might just be one bubble in this infinite froth, a single note in a symphony of multiverses. Inflation's math suggests that once it starts, it doesn't stop. It keeps creating pocket universes endlessly, like a cosmic conveyor belt churning out realities. Some might have stronger gravity, others might lack dark matter, and a few could be so alien that matter as we know it never formed. Now, here's where it gets even stranger. The regions between these bubbles aren't empty, they're seething with inflating space, stretching so fast that light from neighboring universes could never reach us. It's like being in a hall of mirrors where every reflection is a self-contained cosmos, forever cut off from our own. And if inflation is truly eternal, then the multiverse isn't just big, it's infinite, with no boundary, no center, and no end. But how do we test something so abstract? The answer lies in the cosmic microwave background. If our universe collided with another bubble in the distant past, it might have left a bruise, a strange pattern in the ancient light. Scientists have scoured the data for these cosmic fingerprints, and while none have been confirmed yet, the search isn't over. Every new telescope peering into the CMB brings us closer to answering whether we're alone in the multiverse or just one page in an endless library of realities. So what does this mean for infinity? If eternal inflation is real, then the universe isn't just larger than we imagined, it's larger than we can imagine. No matter how far you traveled, you'd never hit a wall. You'd just find more space, more bubbles, more universes stretching into eternity. And that raises a haunting question. If the multiverse is infinite, then somewhere out there, every possible version of you and every possible version of everything might already exist. The cosmos isn't just big, it might be boundless. Now let's talk about the universe's silent puppeteer, dark energy. This mysterious force makes up about 68% of the cosmos, and it's doing something downright bizarre, pushing galaxies apart faster and faster as time goes on. Imagine blowing up a balloon with tiny dots on its surface. At first, those dots drift apart slowly, but then something shifts. The balloon starts inflating with such force that the dots suddenly race away from each other, not just steadily but accelerating. That's dark energy in action, and it throws a wrench into everything we thought we knew about the universe's fate. For decades, scientists assumed the cosmos would either expand forever at a steady pace or eventually collapse back in on itself. But dark energy changed the game. In the late 1990s, astronomers studying distant supernova made a shocking discovery. The universe wasn't just expanding, it was speeding up. It was like tossing a ball in the air and watching it shoot toward the sky instead of falling back down. This revelation flipped cosmology on its head, introducing two chilling possibilities for how it all might end. First, there's the Big Rip, a scenario where dark energy's push grows so powerful that it overcomes gravity, electromagnetism, even the nuclear forces holding atoms together. Picture a universe where first galaxies, then stars, then planets are torn apart. Eventually, atoms themselves would be shredded, leaving behind a cold, empty void. It's the ultimate cosmic demolition where space itself frays at the seams. But there's another, quieter doom, heat death. Here, dark energy keeps expanding the universe but at a less violent pace. Galaxies drift beyond each other's horizons, stars burn out, and black holes slowly evaporate. Over trillions of years, the cosmos cools to near absolute zero, a vast graveyard where even time loses meaning. No explosions, no dramatic collapses, just an endless, silent fade. So which fate awaits us? The answer lies in dark energy's true nature. Is its strength constant, or could it grow stronger over time? Right now, the evidence points toward a constant force favoring heat death. But if dark energy is more dynamic, if it's something theorists call phantom energy, then the Big Rip becomes terrifyingly plausible. Here's the twist: we don't actually know what dark energy is. Is it an unchanging property of space itself, like Einstein's cosmological constant? Or is it a shifting field that could someday vanish or spike? Every telescope pointed at the cosmos is hunting for clues, from subtle changes in galaxy clusters to minute ripples in spacetime. The stakes couldn't be higher. The universe's ultimate size and its final moments depend entirely on this invisible, enigmatic force. And that's the irony. The more we learn, the clearer it becomes. Dark energy isn't just shaping the universe's future. It's reshaping the very question of whether infinity is out there, or whether even infinity has an expiration date. If dark energy is the universe's silent architect, quantum mechanics might be its wild card, shaking up the very foundation of reality at the smallest scales. Picture this: empty space isn't truly empty. At the quantum level, particles and antiparticles blink in and out of existence like cosmic static, borrowing energy from the void in fleeting bursts. These quantum fluctuations aren't just microscopic quirks. They might hold the key to understanding whether infinite parallel universes could bubble up from nothingness. Now take that idea and stretch it across the cosmos. Some theories suggest that during inflation, these tiny quantum ripples were stretched to astronomical sizes, becoming the seeds for galaxies. But what if they did more than that? What if certain fluctuations were so extreme they pinched off entire pockets of space-time self-contained universes with their own laws of physics? This is the mind-bending premise of quantum foam cosmology, where the fabric of reality isn't smooth but froths with potential universes, each a fleeting possibility in an endless sea. String theory takes this even further. Imagine the universe isn't built from particles but from vibrating strings, each frequency dictating the properties of matter and energy. The math suggests these strings could exist in a landscape of 10 to the 500 possible configurations, a vast multiverse where every version of physical laws plays out. Some universes might have gravity too weak for stars to form, others could collapse instantly. Ours, with its Goldilocks perfect constants, would just be one lucky roll of the cosmic dice. Here's where it gets even stranger. If inflation and quantum foam keep spawning universes, and string theory's landscape allows for infinite variations, then somewhere out there, a version of you might be reading these words in a universe where gravity is stronger, light is slower, or time runs backward. It sounds like science fiction, but the equations don't lie. These ideas emerge naturally from the marriage of quantum mechanics and general relativity. The catch: we can't observe these alternate realities directly. They're hidden behind the veil of our cosmic horizon, like shadows on the wall of Plato's cave. But some physicists argue that subtle fingerprints might linger in the cosmic microwave background, anomalies that hint at collisions with other bubble universes. Others hunt for evidence in particle accelerators, searching for exotic particles that could only exist if extra dimensions predicted by string theory are curled up invisibly around us. So is the multiverse science or speculation? For now, it's a dazzling hypothesis, a glimpse into how wildly creative reality might be. Whether it's quantum foam, string theory's landscape, or something even stranger, one thing's clear: the universe's true scale isn't just about space, it's about possibilities. And that might be the most infinite thing of all. Imagine stepping outside on a moonless night, staring up at a sky so dark it feels like velvet. Now picture the opposite, a night where every inch of blackness is replaced by the blazing light of countless stars, turning darkness into daylight. That's what the night sky should look like if the universe were infinite, static, and packed with stars stretching endlessly in every direction. This is Olbers' paradox, a question that haunted astronomers for centuries. Why isn't the night sky unbearably bright? The paradox gets its name from Heinrich Olbers, who framed it in the 1800s, but the puzzle dates back even further. Kepler and Halley wrestled with it too. Here's the crux: if the universe is infinite and unchanging, every line of sight you trace upward should eventually land on a star, like standing in an infinite forest where every gap between trees is filled by more trees. The entire sky should glow as brightly as the surface of the sun, bathing Earth in perpetual starlight. Yet the night remains dark, speckled with stars, but far from luminous. So what's the trick? Modern cosmology reveals two game-changing answers. First, the universe isn't static, it's expanding. Edwin Hubble's groundbreaking observations showed galaxies racing away from us, their light stretched into longer, redder wavelengths by the stretching of space itself. This redshift means the light from the most distant stars loses energy as it travels, dimming to near invisibility by the time it reaches us. Even if infinite stars exist, their light fades into the infrared and beyond, like voices swallowed by an ever-widening canyon. But there's a second, even more profound reason. The universe has a finite age. Light travels at a cosmic speed limit, 300,000 kilometers per second, meaning the light we see today has only had so much time to reach us since the Big Bang, 13.8 billion years ago. Beyond a certain point, light from more distant stars simply hasn't arrived yet. It's like being in a stadium where the crowd's cheers take time to reach you. The voices from the farthest seats haven't had time to cross the distance. This creates a horizon, the observable universe, beyond which we can't see, no matter how powerful our telescopes. And here's the kicker. If you combine these two facts, the universe's expansion and its finite age, you'd still expect a bit more light than we actually see. That's where cosmic inflation comes in. The universe's explosive initial growth stretched space so rapidly that vast regions were pushed beyond our horizon, their light forever out of reach. What's left in our observable bubble is just a fraction of what could be out there, leaving the night sky deliciously, mysteriously dark. So the next time you gaze up at the stars, remember, the darkness between them isn't empty. It's a cosmic message written in the language of expansion and time, telling us the universe is far stranger and far more dynamic than we ever imagined. The idea of a multiverse isn't just one theory, it's a whole spectrum of possibilities, each more mind-bending than the last. The simplest version is the level 1 multiverse, born from a straightforward truth. If space is truly infinite, then somewhere out there, every possible configuration of matter must repeat. Think of it like shuffling a deck of cards. If you do it enough times, the same order will eventually appear again. In an infinite cosmos, there's not just one Earth with your life playing out. There are infinite Earths, infinite versions of you, some nearly identical, others wildly different. It's not science fiction. It's the logical consequence of endless space combined with finite quantum possibilities. But here's the catch. Even if these parallel worlds exist, they're so far beyond our cosmic horizon that we'll never see them. The universe's expansion pushes them away faster than light could ever bridge the gap. Then there's level 2, the multiverse of inflationary bubbles. Remember how cosmic inflation stretched our universe from smaller than an atom to something incomprehensibly vast? What if that process never stopped? Picture a foaming ocean where new universes constantly nucleate like bubbles in boiling water, each with its own physics. Some might have stronger gravity, making stars burn out in moments. Others could have no dark matter, leaving galaxies to drift apart. Our universe, with its seemingly perfect constants for life, might just be a lucky accident in an endless froth of failed experiments. This isn't idle speculation. The math of eternal inflation predicts it. And if it's true, infinity isn't just about space, it's about realities, an endless tree branching into every possible universe that physics allows. But the wildest twist comes with level 3, the quantum many-worlds interpretation. Every time a particle faces a choice, like whether to spin left or right, quantum mechanics says it doesn't choose. Instead, reality splits, creating two versions of the universe, one where it spun left, another where it spun right. Apply this to every quantum event, and you get a mind-blowing tapestry of branching timelines. Did you turn left at the intersection this morning? Somewhere, another you turned right. Did a star explode 1 billion years ago? In another branch, it didn't. Unlike level 1's distant duplicates or level 2's alien physics, these parallel worlds exist right here, overlapping with ours but forever out of reach. So does infinity just shift to a higher level? In a way, yes. Whether it's infinite space birthing identical copies, eternal inflation spawning universes with new laws, or quantum splits creating endless timelines, the multiverse redefines what everything could mean. But here's the haunting question. If these layers of infinity are real, how could we ever prove it? Some scientists search for cosmic bruises, imprints of other bubble universes colliding with ours in the ancient past. Others look for anomalies in the quantum foam, hints that our reality isn't as standalone as it seems. And some argue that the multiverse isn't science at all, just an untestable hypothesis dressed in equations. Yet the allure remains. The multiverse doesn't just expand the cosmos, it explodes the very idea of reality, suggesting that all possibilities, no matter how strange, exist somewhere. Infinity isn't just vast, it's layered, nested, and perhaps more astonishing than we've dared to imagine. Mathematics gives us infinity, an idea so clean, so boundless that it fits neatly into equations. But does infinity exist beyond the chalkboard? The debate splits scientists down the middle. On one side, you've got thinkers like Max Tegmark, who argue that infinity isn't just real, it's inevitable. His mathematical universe hypothesis flips the script entirely. If reality is fundamentally mathematical, then every structure math allows must exist somewhere. In this view, infinity isn't an abstraction, it's the cosmic default. Our universe, with its specific laws, is just one page in an endless textbook of mathematical possibilities. Want a universe where gravity runs backward or time loops like a Möbius strip? Tegmark's framework says it's out there because the math permits it, but critics fire back with a simple question: where's the evidence? Infinity might work in theory, but physics deals in measurable, testable truths. Take the cosmological constant, the number representing dark energy's strength. If the universe were truly infinite, why does this constant have such an oddly precise, finite value? A tweak too high and galaxies never form, too low and everything collapses. This fine-tuning problem suggests something deeper. Maybe infinity is a crutch, a placeholder for gaps in our understanding. After all, nature abhors true infinities. Black holes, their densities approach infinity at the singularity, but we've never observed one actually reaching it. Even the Big Bang, once thought of as an infinite point, now gets treated as a quantum fuzz where classical physics breaks down. Then there's the pragmatic camp scientists who see infinity as a useful fiction. Think of it like a line of dominoes stretching forever. You'll never knock them all down, but pretending they go on infinitely helps you model their behavior. That's how physicists often use infinity, as a tool to simplify calculations about cosmic expansion or quantum fields. But tools aren't truths. As Nobel laureate Roger Penrose puts it, the universe isn't obliged to conform to mathematical elegance. Reality might be messy, finite, and far stranger than our neat symbols suggest. This tension isn't just academic, it reshapes how we see existence. If infinity is real, the cosmos is a kaleidoscope of limitless variations. If it's not, then every mystery, from dark energy to quantum foam, has a solution hidden in the finite fabric of space. For now, the question lingers: is infinity the universe's true nature, or just the reflection of a mind trying to grasp the ungraspable? One thing's certain: math and physics are still learning to speak the same language. Until they do, infinity remains the most tantalizing mirage in science, always on the horizon, never quite within reach. While string theory and cosmic inflation dominate discussions about infinity, there's another player on the field with a radically different vision: loop quantum gravity. Forget smooth, continuous space. This theory paints the universe as a fabric woven from tiny, indivisible threads, like a cosmic tapestry where each stitch is a Planck-length loop of spacetime itself. If this is true, then infinity might not just be out of reach, it might be impossible. At the heart of loop quantum gravity is the idea that space isn't infinitely divisible. Just as you can't split an atom without changing its fundamental nature, you can't slice spacetime beyond a certain scale. Picture a digital photo, zoom in far enough, and you hit pixels, the smallest units that make up the image. Loop quantum gravity suggests spacetime works the same way, with a pixelated structure at the Planck scale. That's 10 to the negative 35 meters for context. These pixels aren't static, they vibrate, twist, and interact, creating the dynamic fabric of reality we experience as gravity. Now, here's where things get truly provocative. If spacetime is granular, then the universe itself might be finite, not because it has an edge like some cosmic wall, but because the total number of these spacetime pixels could be staggeringly large yet countable. Think of it like a balloon made of a finite number of rubber bands. The balloon can expand, but it's still built from a limited number of components. In this framework, the universe's expansion isn't about stretching into nothingness. It's about the network of loops rearranging, creating more space without requiring infinite ingredients. This clashes dramatically with mainstream cosmology. Most models treat space as smooth and continuous, borrowing from Einstein's general relativity, where space-time bends and warps like a rubber sheet. But loop quantum gravity argues that at the tiniest scales, relativity breaks down and quantum effects take over. It's like comparing ocean waves to individual water molecules. Both describe the same thing, but at different resolutions. So how does this theory tackle the Big Bang? In a stunning twist, loop quantum gravity suggests there might not have been a singularity, a point of infinite density at all. Instead, the universe could have bounced from a previous collapsing phase, like a cosmic rubber band snapping back. This big bounce scenario replaces the fiery beginning with a transformational moment, sidestepping infinity entirely. But here's the catch: if spacetime is granular, does that mean the universe has a finite volume? The answer is maybe. Some loop quantum gravity models hint that while space is quantized, the number of possible configurations could be so vast it's practically infinite. It's like counting grains of sand on a beach, technically finite but functionally limitless. Critics, though, point out the gaps. Unlike string theory, which aims to unify all forces of nature, loop quantum gravity focuses narrowly on gravity's quantum nature. It doesn't yet explain dark energy, the standard model particles, or why the cosmos looks so uniform. And without direct experimental evidence, like detecting spacetime's pixels, the theory remains a compelling what-if. Yet that's what makes it so electrifying. Loop quantum gravity doesn't just challenge infinity, it reimagines the universe's very architecture. Whether it's right or wrong, it forces us to ask, is infinity a physical reality or just a mathematical convenience? The answer might lie not in distant galaxies, but in the quantum weave of spacetime itself. What if everything you see, the stars, galaxies, even the screen in front of you right now, isn't quite as three-dimensional as it seems? The holographic principle turns our perception of reality inside out, proposing that the universe might actually be a two-dimensional surface projecting the illusion of depth like a cosmic IMAX screen. It's not just a wild thought experiment, it's a serious theory with roots in one of the most mysterious places in existence, the event horizon of a black hole. Let's start with black holes, those cosmic vacuum cleaners where gravity is so strong not even light can escape. In the 1970s, physicist Jacob Bekenstein made a startling discovery. A black hole's entropy, a measure of disorder or information, isn't determined by its volume, but by the area of its event horizon, the point of no return. This was bizarre. Normally, entropy scales with volume. Think of how many more ways you can arrange furniture in a large room versus a small one, but black holes play by different rules. Their information content seems painted onto their surfaces, not stuffed inside. This oddity caught the attention of Nobel laureate Gerard T. Hooft and Leonard Susskind, who took the idea further. If a black hole's entropy is bound to its surface area, maybe all the information in the universe works the same way. Imagine a room covered floor to ceiling in tiny pixels, each holding a bit of data. The holographic principle suggests our three-dimensional reality could be a projection from a two-dimensional boundary, like a hologram floating above a flat plate. Every particle, every force, every ripple of gravity might just be data etched onto the edges of the cosmos. Here's where it gets even stranger. If the universe is holographic, there's a hard limit to how much information any given region of space can contain, just like there's a limit to how many pixels can fit on your phone's screen. This means reality might be fundamentally pixelated, with no such thing as true continuity. Zoom in far enough and you'd hit the universe's resolution limit, Planck-scale pixels of spacetime beyond which no finer detail exists. But how could a flat surface encode something as rich as a three-dimensional world? Think of a credit card hologram, tilt it, and the image shifts as if it has depth, even though it's just light interacting with microscopic patterns on a flat sticker. The holographic principle argues that the universe does something similar using quantum entanglement. the spooky link between particles across vast distances to stitch together a convincing illusion of depth. Now, the million-dollar question: where is this two-dimensional boundary? Some theories place it at the edge of the observable universe, far beyond where light has had time to reach us. Others suggest it's woven into the fabric of space itself, like a hidden layer of code running beneath reality's graphics. Either way, if the holographic principle holds, it would mean the universe isn't just finite, it's efficient, packing all its complexity into the ultimate cosmic zip file. And here's the kicker: this isn't just philosophy. Experiments like the holometer at Fermilab have hunted for evidence of this pixelation by looking for quantum jitters in spacetime itself, tiny fluctuations that might betray the universe's underlying grid. So far, no smoking gun, but the search isn't over. The holographic principle forces us to confront a humbling possibility. The richness of our three-dimensional experience might just be the universe's most dazzling magic trick. Zoom out far enough, and the universe reveals its hidden skeleton, a colossal web of galaxies strung along luminous filaments, separated by unimaginably vast voids. These aren't just empty spaces, they're cosmic deserts stretching hundreds of millions of light years, where matter is so sparse you could cross them and barely encounter a single star. Yet these voids aren't random. They're part of an intricate pattern, the universe's large-scale structure, and decoding it might hold the answer to whether we're living in a finite cosmos or an infinite one. Picture the universe as a loaf of raisin bread baking in the oven. As the dough expands, the raisin's galaxies move apart, but they also cluster along stretch marks in the dough, forming filaments. The voids, those are the empty pockets between. Galaxy surveys like the Sloan Digital Sky Survey have mapped millions of these structures, revealing a foam-like architecture where galaxies cling to the edges of bubbles like dew on a spiderweb. The startling part: this pattern isn't chaotic. It follows precise mathematical rules, echoing the faint density fluctuations left over from the Big Bang. But here's the mystery: if the universe is infinite, why does this web appear so consistent? In an endless cosmos, you'd expect wild variations, regions where filaments stretch endlessly and others where voids dominate. Yet no matter where we look, the cosmic web looks eerily similar, like a fractal repeating its pattern at different scales. Some theorists argue this could hint at a finite universe, one where space loops back on itself like a video game world. If you traveled far enough in a straight line, you might end up where you started, encountering the same structures again and again. Others see a darker possibility, that we're simply too small to perceive the true scale of infinity. Imagine an ant crawling on a beach. To the ant, a few grains of sand might seem like a vast desert, while the real ocean lies just beyond its perception. Similarly, our observable universe, 93 billion light-years across, might be a single stitch in an infinite tapestry, its patterns accidental rather than cosmic law. The most tantalizing clues come from the cosmic microwave background's faint imprints. If the universe were finite, certain patterns in this ancient light should repeat like echoes in a mirrored room. So far, no such echoes have been confirmed, but the search isn't over. Upcoming telescopes like the European Space Agency's Euclid mission could finally spot irregularities that betray the universe's true shape. Until then, the voids and filaments remain a paradox, both a map and a mirage. They might be the fingerprints of a finite cosmos, or just the first brushstrokes on an infinite canvas. Either way, one thing's certain: the universe's structure isn't just telling us how it's built, it's whispering what it truly is. If the universe truly is infinite, or at least lasts for an unimaginably long time, then according to the laws of probability, every possible event must happen eventually. Not just once, but an infinite number of times. That includes wildly improbable things like a deck of cards shuffling itself into perfect order by chance, or a tornado assembling a fully functional airplane from scrap metal. But here's where it gets unsettling. In an eternal cosmos, the most statistically likely conscious experience might not be a human body living on a planet. It might just be a lone, disembodied brain floating in the void, hallucinating reality into existence. This is the Boltzmann Brain paradox, named after physicist Ludwig Boltzmann, who first grappled with the eerie connection between thermodynamics and infinity. The idea hinges on entropy, the tendency of the universe to move from order to disorder. Given enough time, even the most chaotic systems will occasionally stumble into order purely by random fluctuations. So in an infinite universe, there's a non-zero chance that particles could spontaneously arrange themselves into a fully conscious brain complete with fake memories of a past, a fake present, even a fake you reading these words right now. And statistically, such freak fluctuations would be vastly more common than the slow, improbable evolution of galaxies, stars, and biological life. Think of it like a monkey randomly typing on a keyboard. Given infinite time, it will eventually produce Shakespeare's Hamlet, but the overwhelming majority of its output will be gibberish, and the simplest coherent phrase, to be, say, will appear far more often than an entire play. Similarly, in the cosmic casino, the odds favor fleeting Boltzmann brains over stable civilizations like ours. So why does reality feel so rich, so consistent, if we're more likely to be hallucinations in the void? Some physicists dismiss Boltzmann brains as absurd, a reductio ad absurdum, revealing flaws in our assumptions about infinity. Others propose fixes, like the idea that eternal inflation's bubble universes have finite lifespans, cutting off the time available for freak fluctuations. But the paradox lingers, forcing us to confront a haunting question. Is the universe older than we think or smaller? Either way, the Boltzmann brain paradox isn't just a thought experiment. It's a stress test for cosmology itself, pitting infinity against the stubborn fact that reality feels real. And that's a puzzle even the most daring physicists can't shake off. The universe seems suspiciously well suited for life. Tweak gravity just a fraction stronger, or adjust the nuclear forces even slightly, and stars wouldn't form, atoms would never bond, and life as we know it couldn't exist. This eerie precision is called the fine-tuning problem, and it's one of the most baffling clues in cosmology. But here's where it gets even stranger. Whether the universe is finite or infinite changes everything about how we interpret this cosmic coincidence. If the cosmos is finite, the odds feel overwhelming against us. Imagine a cosmic dartboard with trillions of possible configurations for physical constants, and only a razor-thin sliver where life can emerge. Landing the dart in that exact spot seems astronomically unlikely unless there's something guiding it. Some see this as evidence for a deeper principle at work, like the strong anthropic principle, the idea that the universe must allow conscious observers like us because otherwise no one would be here to wonder about it. It's less a scientific explanation and more a philosophical shrug, but in a finite universe it's hard to avoid. Now flip the script. What if the universe is infinite? Suddenly, those impossible odds don't just shrink, they vanish. In an endless expanse, every possible combination of physical constants must exist somewhere. There'd be regions where gravity crushes stars instantly, others where matter never clumps into planets, and inevitably pockets like ours where conditions are just right. In this view, life isn't a miracle. It's a statistical certainty guaranteed by the sheer scale of existence, but infinity comes with its own existential vertigo. If every possible version of reality plays out somewhere, does our existence lose meaning, or does it become even more astonishing, a fleeting spark in an eternal ocean of possibilities? Some argue that infinity amplifies life's significance, making us witnesses to an unfathomable cosmic lottery. Others counter that it renders us cosmically insignificant, one accidental arrangement in an endless sea of failures. Here's the twist: we might never know for sure. Even if the universe is infinite, we're trapped in our tiny observable bubble, forever cut off from the greater whole. The fine-tuning debate becomes a mirror reflecting not just the universe's mysteries but our own hunger for purpose. Whether finite or infinite, the cosmos keeps its deepest secrets close, leaving us to wonder if we're the universe's intended audience or just an incidental footnote in an epic too vast to comprehend. Time adds another layer to the mystery of infinity, because if the universe had a beginning, can space truly stretch forever? The Big Bang suggests a fiery starting point 13.8 billion years ago, but here's the twist. Just because time here had a beginning doesn't necessarily mean space has edges. Think of it like a movie reel. The film might have a first frame, but the screen it's projected onto could be endless. Some cosmologists argue the Big Bang wasn't the birth of everything, just the start of our cosmic chapter, leaving open the possibility that space itself extends infinitely beyond what we can observe. But what if time isn't linear at all? Enter Roger Penrose's conformal cyclic cosmology, a theory so radical it redefines both beginnings and endings. Penrose proposes that the universe doesn't have a single timeline but cycles through infinite epochs, each ending in a heat death so complete that all particles lose their sense of scale, resetting conditions for a new Big Bang. In this model, infinity isn't about space alone. It's about time looping eternally, like a cosmic phoenix rising from its own ashes. The eerie part, Penrose claims to have found evidence of these past universes in the cosmic microwave background, circular patterns he calls Hawking points, echoes of black holes from a previous cycle. Then there's the bouncing universe hypothesis, where expansion and collapse alternate like breaths. Imagine the universe as a rubber band stretching to its limit, then snapping back into a singularity only to rebound in a new Big Bang. Unlike Penrose's heat-death reset, these bounces preserve some traces of the past, meaning each cycle might not be a total fresh start. Some versions of this theory even suggest quantum effects could prevent a true singularity, smoothing the transition between cycles like a cosmic trampoline. The implications are staggering. If time is cyclical, the question shifts from, is the universe infinite, to how many universes have there been? Infinity becomes less about space and more about repetition, an endless drumbeat of creation and destruction. But here's the catch. These models rely on exotic physics, from quantum gravity to hidden dimensions, and not all scientists are convinced. Critics argue that without direct evidence of a pre-Big Bang universe, cyclic theories remain elegant speculation. Yet they force us to confront a deeper truth. Infinity might not be a place but a process. Whether it's Penrose's timeless cycles or the eternal bounce of quantum cosmology, time itself could be the key to unlocking the universe's ultimate scale. And that leaves us with a humbling thought. If time is infinite, then every ending is just a prelude to another beginning. The cosmos isn't just big, it's relentless. What if the universe isn't just vast, what if it's rendered? The simulation hypothesis suggests that everything we perceive, stars, galaxies, even our own consciousness, might be nothing more than lines of code in an unfathomably advanced computer. If that's true, then the concept of infinity takes on a bizarre new meaning. Instead of an endless expanse of physical space, infinity could simply be an illusion created by procedural generation, like a video game that crafts limitless terrain on the fly, only rendering what the player sees. Nick Bostrom's famous trilemma lays out the unsettling possibilities. Either civilizations never reach the technological stage to run ancestor simulations, they choose not to, or we're already in one. If the third option holds, then the universe's apparent scale might just be a clever optimization trick. Think of open-world games like No Man's Sky, where algorithms generate quintillions of planets without requiring a galaxy's worth of storage. The cosmos could work the same way, only simulating the parts we observe, with the rest existing as mathematical potential until someone or something looks. But here's the catch, even simulations have limits. Computational power isn't infinite, and an ancestor simulation would need to prioritize efficiency. That's why some theorists argue we'd find clues in the universe's underlying resolution. Quantum mechanics already hints at this: particles behave differently when observed, as if the simulation is conserving resources by only calculating definite states when necessary. And if spacetime is pixelated at the Planck scale, that could be the rendered distance of reality itself. Yet the simulation angle flips infinity on its head. If the universe is a construct, its boundaries aren't defined by physics but by the computational capacity of the system running it. An infinite cosmos might just be a looped or recursive algorithm, replaying variations of the same patterns to create the illusion of boundlessness. Even dark energy could be a failsafe, a way to prevent civilizations from spreading too far and overloading the simulation's memory, the real mind bender. If we're in a simulation, the creators might also be simulated, nested in layers of reality like Russian dolls. Infinity wouldn't be a property of space but of recursion, an endless stack of simulations within simulations, each oblivious to the level above. So the next time you gaze at the night sky, ask yourself, are you looking at the edge of the universe or just the edge of the render? Long before telescopes or quantum physics, the human mind wrestled with infinity not as a scientific concept but as a philosophical labyrinth. Aristotle was among the first to draw a line in the sand, distinguishing between potential and actual infinity. To him, infinity wasn't a thing you could point to but a process, like counting numbers endlessly. You could always add one more, but that didn't mean infinity existed as a completed whole. This idea clung to Western thought for centuries, shaping how early cosmologists viewed the cosmos. Even as astronomers mapped the heavens, many still saw the universe as a finite bubble, because an actual infinity, a truly endless space, felt like a paradox waiting to collapse under its own weight. Then came Immanuel Kant, who turned infinity into a mirror for human limitation. In his critique of pure reason, he argued that infinity isn't something we encounter in experience. It's a category our minds impose to make sense of the world's boundlessness. Imagine standing on a shore, watching the horizon stretch farther than your eyes can see. Kant would say that horizon isn't out there, it's a projection of your mind's inability to conceive an endpoint. This tension between what we observe and what we're capable of imagining still echoes in modern cosmology. When physicists debate whether the universe is infinite or just unfathomably large, they're replaying Kant's ancient dilemma. Is infinity a property of nature or a quirk of perception? The leap from philosophy to physics came with Georg Cantor, a mathematician who dared to treat infinity as something tangible. In the late 19th century, he proved that not all infinities are equal, some are larger than others. The infinite set of whole numbers, for example, is dwarfed by the infinite set of decimals between 0 and 1. Cantor's work shattered Aristotle's tidy dichotomy, suggesting infinity wasn't just a theoretical label but a layered, almost tactile reality. Suddenly, cosmology had a new vocabulary. If space is infinite, which kind of infinite is it? A countable procession of galaxies or an uncountable ocean of dimensions? Yet even Cantor's breakthroughs couldn't resolve the visceral unease infinity provokes. Take the ancient paradox of the grain heap. Remove one grain at a time, and at what point does it stop being a heap? Now scale that up to the cosmos. If the universe is infinite, does removing a galaxy or a billion galaxies change its essential nature, or does infinity swallow all differences, rendering human scale logic meaningless? This isn't just academic navel-gazing, it cuts to the heart of whether the universe operates by rules we can ever fully grasp. Modern cosmology leans into the discomfort. The potential infinity Aristotle rejected now lurks in theories like eternal inflation, where new universes bubble up endlessly. Meanwhile, the actual infinity Cantor championed haunts models of a spatially boundless cosmos. The irony, both perspectives might be describing the same reality, just through different lenses. After all, if the universe is a hologram, as some theories suggest, its infinity could be encoded on a finite surface, blending Aristotle's caution with Cantor's daring. So where does that leave us, staring into the night sky, armed with equations and thought experiments, still asking the same question that troubled the ancients? Is infinity out there or in here? The answer might lie somewhere in between, a cosmic riddle woven into the fabric of both the universe and the minds trying to understand it. Across cultures and millennia, humanity's search for cosmic meaning has taken wildly different shapes, none more vivid than the churning, cyclical vastness of Hindu cosmology versus the linear creation saga of Abrahamic traditions. Picture a dancer performing the same steps over and over, not because they're stuck, but because the dance itself is eternal. That's the essence of Hindu cosmology, where time isn't a straight line but a wheel turning through endless cycles of creation, preservation, and dissolution. Each day of Brahma, lasting 4.32 billion years, sees universes bloom and fade like bubbles on the surface of a boundless ocean, only for the cycle to begin anew. There's no ultimate beginning or end, just the infinite rhythm of existence itself. Now contrast that with the Abrahamic vision, Judaism, Christianity, and Islam, where creation has a definitive starting point. In Genesis, the universe springs forth from divine command in 6 days, launching a linear march toward a promised culmination: Judgment Day, Paradise, or Messianic Age. Time here is an arrow, not a circle. The cosmos might be vast, but it's traveling somewhere toward redemption, restoration, or divine reunion. This linearity shapes everything from Western scientific thought to our instinctive question, how did it all begin? For Hindu traditions, that question almost doesn't compute, like asking when the first breath was taken in a room where people have always been breathing. But here's where these worldviews collide in unexpected ways. Hindu texts describe a multiverse long before modern physics, with countless parallel worlds, lokas, operating on different vibrational planes. Meanwhile, medieval Jewish mystics envisioned the Kabbalistic Tzimtzum, where God withdraws to make space for creation, an eerie parallel to cosmic inflation's stretching void. Both traditions grappled with infinity, one embracing it as natural, the other seeing it as a veil between creator and creation. Cultural lenses don't just shape answers, they redefine the questions themselves. Where a scientist might ask, is the universe finite? A Hindu rishi could counter, which universe? And an Abrahamic theologian might ponder, why is there something rather than nothing? These aren't just philosophical quirks, they're proof that infinity, like light through a prism, fractures into different colors depending on who's holding the glass. And in that spectrum lies a truth more profound than any single perspective. The universe might be absolute, but our wonder is endlessly diverse. The next generation of telescopes isn't just sharpening our view of the cosmos, it's poised to crack open the universe's deepest secrets, from its curvature to its ultimate scale. Leading the charge is the James Webb Space Telescope, already revolutionizing astronomy with its infrared gaze, but Webb is just the opening act. Missions like Japan's Lightbird, set to launch in the late 2020s, are designed to scrutinize the cosmic microwave background with unprecedented precision, hunting for faint distortions that could reveal whether space bends back on itself or stretches forever. Imagine examining a seemingly flat sheet of paper under a microscope, only to discover it's covered in microscopic bumps and valleys. Lightbird's goal is to find those cosmic wrinkles, evidence that the universe might be finite after all. Then there's the European Space Agency's Euclid mission, mapping the three-dimensional distribution of galaxies across 10 billion light-years. By tracing how dark energy alters the growth of cosmic structures over time, Euclid could uncover whether the universe's expansion rate varies in ways that hint at a larger, unseen geometry. Think of it like measuring the ripples in a pond to deduce the shape of the lake beneath, except the pond is the observable cosmos, and the lake might be infinite. But perhaps the most tantalizing possibility lies in the hunt for primordial gravitational waves, ripples in spacetime from the universe's first moments. Projects like the future Big Bang observer aim to detect these echoes, which could carry imprints of cosmic inflation's ultimate scale. If these waves exhibit specific patterns, like a preferred direction or wavelength cutoff, they might betray whether our universe is a single bubble in an infinite multiverse or a self-contained cosmos with finite volume. The irony, even as these telescopes push boundaries, they might only deepen the mystery. A perfectly flat universe could still be finite but unimaginably large, like an ant crawling on a balloon so vast it feels flat. Conversely, a slight curvature wouldn't guarantee finiteness, just a universe that loops on scales far beyond our horizon. The real breakthrough may come not from a single observation, but from piecing together clues across multiple experiments, like assembling a cosmic jigsaw where every new piece changes the picture. What's certain is this: within the next decade, we'll either corner infinity or discover it's been slipping through our fingers all along. String theory dances on the edge of paradox, suggesting that the universe we experience, with its 3 spacious dimensions and 1 of time, might just be the tip of an iceberg. Hidden beneath the surface could lie 6 or 7 extra dimensions, curled up into shapes so tiny, so intricate, they evade detection. These are the Calabi-Yau manifolds, theoretical geometric forms named after mathematicians Eugenio Calabi and Xing-Tung Yau, and they might hold the key to whether the cosmos is finite or infinite in ways we've never imagined. Picture a garden hose stretched across a field. From a distance, it looks like a simple one-dimensional line, but zoom in close and you'll see its surface is actually a 2-dimensional cylinder wrapped tightly around itself. Calabi-Yau shapes take this idea to cosmic extremes. They're like the hose's hidden dimension, but far more complex, twisted, folded, and knotted into 6-dimensional spaces smaller than a single atom. If string theory is correct, every point in our familiar 3-dimensional space could harbor one of these minuscule origami structures, vibrating with the frequencies that give rise to particles, forces, even the fabric of reality itself. Now here's where infinity gets tangled. If these extra dimensions are compact, finite, and self-contained, like the surface of a marble, then our observable universe might also be finite, just nested within something vastly larger. Imagine a soap bubble floating in an endless sky. The bubble's surface is finite, but the space around it stretches infinitely. Similarly, our universe could be a finite membrane, a brain in string theory jargon, drifting in a higher dimensional bulk that goes on forever. In this scenario, infinity isn't a property of our universe but of the arena it inhabits. But there's a twist. Some versions of string theory suggest these hidden dimensions might not be strictly finite. Certain Calabi-Yau shapes have holes or tunnels connecting different regions, like a cosmic Swiss cheese. If those tunnels stretch indefinitely, or if the shapes themselves can unfurl into higher dimensions, then even our tiny, curled-up extra dimensions could be gateways to infinities we can't perceive. It's like discovering your closet doesn't just hold coats, it's a doorway to another universe. The implications are dizzying. If extra dimensions are finite, they could cap the total size of our universe, placing hard limits on how much space and energy it contains. But if they're infinite, or if they connect to higher dimensional infinities, then our cosmos might be a speck in an unfathomably vaster structure. The catch: we've yet to find any experimental proof of these hidden dimensions. Particle colliders like the Large Hadron Collider hunt for clues in high-energy collisions, hoping to spot particles that momentarily leak into these dimensions. So far, no luck, yet the math keeps pulling us deeper. String theory's equations don't just allow for Calabi-Yau manifolds, they require them, like keys fitting into cosmic locks. And if those shapes determine the universe's fundamental constants like the strength of gravity or the mass of electrons, then their geometry might explain why our reality is so finely tuned for life. A slight change in the twist of a Calabi-Yau fold could mean a universe where atoms never form, where stars never ignite. So are we living in a finite universe stitched into an infinite higher dimensional tapestry? Or is infinity woven into the very fabric of our reality, hiding in dimensions too small to see? Until we can peer deeper, perhaps with quantum gravity experiments or signatures in the cosmic microwave background, the question remains suspended between equations and imagination. One thing's certain, if string theory's hidden dimensions are real, they're rewriting the rules of what finite and infinite even mean. Black holes are cosmic paradoxes, regions where gravity crushes matter into oblivion, yet quantum mechanics insists nothing truly disappears. This contradiction lies at the heart of the black hole information paradox, a puzzle so profound it challenges our understanding of space-time itself. Picture tossing a book into a black hole. According to Einstein's general relativity, that book is gone forever, its information shredded by the singularity. But quantum mechanics rebels, declaring information can never be destroyed, only scrambled. So where does the truth lie? The answer might rewrite the rules of reality, revealing whether the universe operates on infinite or finite principles. Enter Hawking radiation, Stephen Hawking's revolutionary insight that black holes aren't entirely black. Quantum fluctuations near the event horizon cause these cosmic monsters to slowly leak particles, evaporating over eons like ice melting in the sun. Here's the catch: if a black hole evaporates entirely, what happens to the information it swallowed? Hawking initially argued it's lost forever, vanishing into the void, a direct violation of quantum mechanics' sacred law of information preservation. This sparked decades of debate, with physicists like Leonard Susskind countering that information must escape, encoded in the radiation itself like a cosmic QR code. The stakes: if information can be lost, the universe might not follow deterministic rules, opening the door to true randomness, even infinities beyond our comprehension. The firewall paradox cranks the tension even higher. Imagine falling toward a black hole's event horizon. According to Einstein, you'd float peacefully, unaware of the point of no return, a principle called no drama. But quantum mechanics suggests a gruesome alternative, an invisible wall of blazing energy just beyond the horizon, incinerating you instantly. This firewall emerges from the clash between information preservation and Einstein's smooth spacetime. If Hawking radiation carries scrambled information away, the horizon must become a violent quantum scrambler to erase any duplicate data, a paradox that leaves physicists torn. Is spacetime fundamentally smooth, or is it pixelated with firewalls marking the seams? Now tie this back to infinity. If information must be preserved, a core tenet of quantum theory, does that imply the universe has finite information storage? A truly infinite cosmos could, in theory, lose information without consequence, like dropping a pebble into an endless ocean. But if every bit of data must be accounted for, perhaps the universe operates like a closed system, its total information capped. Some theories even suggest black holes might be holograms, their information painted on a two-dimensional surface like a cosmic hard drive, hinting at a finite, pixelated reality beneath the illusion of smooth spacetime. The implications ripple outward. If black holes preserve information, they might be the universe's ultimate recyclers, encoding swallowed stars into Hawking radiation like cosmic printers. But if information vanishes, it could mean spacetime itself is more malleable or flawed than we thought. The paradox forces us to ask, is the universe a flawless quantum ledger, or does it allow gaps where infinity swallows the rules? Until we crack this puzzle, black holes remain the ultimate cosmic locks, guarding secrets that could redefine everything from entropy to the nature of existence itself. And that's the beauty of the paradox. It doesn't just challenge physics. It challenges us to rethink what reality really is. If every possible version of you exists across an infinite cosmos, what happens to the idea of you? The concept of identity starts to unravel when stretched across endless realities. Imagine a universe where another you made different choices, skipped that job interview, never met their partner, took that flight that crashed. In an infinite multiverse, all those versions exist simultaneously. So who's the real you, the one watching this video right now, or the version in a parallel world living a completely different life? This isn't just a thought experiment, it's an existential earthquake shaking the foundations of selfhood. And then there's the ethical weight. If every decision branches into infinite outcomes, does moral responsibility dissolve? If a version of you commits an atrocity in some distant corner of the multiverse, does that stain your conscience, or does culpability get diluted across the infinite spectrum of possibilities? Philosophers call this the problem of moral luck, the unsettling idea that the morality of an action might depend on sheer chance rather than intent. In a finite world, we hold people accountable for their choices. But in an infinite one, every choice is made and unmade somewhere. Even more chilling is the question of suffering. If the universe is infinite, then every conceivable tragedy, every war, every plague, every personal agony must replay endlessly across the cosmic tapestry. The Holocaust isn't a singular historical horror, it's a fixed point in an eternal recurrence. Does that make the universe inherently cruel, or does it render pain meaningless through sheer repetition? Some argue that infinity forces us to confront the absurd, that existence has no grand narrative, just infinite variations without resolution. Yet there's a flip side. If every possible version of happiness also exists, every joy, every triumph, every act of love, does that redeem the cosmos's scale? The same infinity that guarantees suffering also ensures that somewhere a version of you is living their best life, surrounded by peace and fulfillment. It's a dizzying trade-off. The price of boundless possibility is the inevitability of boundless despair. Perhaps the only way to reconcile this is to shrink the frame, to focus not on the infinite but on the immediate. Even if a trillion other yous exist, this version's choices still matter to you here, now. Infinity might render identity fluid, but consciousness remains anchored in the present. The ethical takeaway: act as if this iteration is the only one that counts, because for you, in this moment, it is. The universe may be endless, but your experience of it is fiercely, beautifully finite. So where does this leave us? After centuries of staring at the stars and decades of crunching the numbers, the debate over infinity still hangs in the cosmic balance. On one side, you've got the sheer vastness of inflation theory, multiverses bubbling into existence faster than light can chase them, and the mathematical inevitability that endless space demands endless repetition. The numbers don't lie. If the universe is infinite, then somewhere out there, every possible version of reality is playing out on loop. Boltzmann brains, alternate Earths, even galaxies made of dark matter we can't begin to imagine. It's a dizzying thought, one that turns the cosmos into the ultimate fractal, repeating its patterns down to the last quantum fluctuation. But then there's the counterargument, the stubborn silence of the data. For all our telescopes and equations, we've yet to find a single smoking gun for infinity. No repeating patterns in the cosmic microwave background, no definitive curvature to space, no echoes of collisions with other bubble universes. The observable universe behaves like a finely tuned, self-contained system. Its constants so precise that some physicists argue infinity isn't just unproven, it's unnecessary. Maybe the cosmos isn't endless. Maybe it's just so colossal that it feels infinite, like an ant trying to map the Pacific Ocean one grain of sand at a time. And that's the heart of the mystery. Infinity isn't just a scientific question. It's a mirror. Does the universe need to be infinite to feel awe-inspiring, or does its very finitude, the idea that it has edges, even if we'll never see them, make it all the more precious? Carl Sagan's pale blue dot reminder hits harder here. Whether we're a speck in an endless cosmic ocean or the sole flicker of light in a vast but finite void, our hunger to understand it matters. The equations might never settle the debate, but the quest itself, the act of looking up and wondering, is what stitches us into the fabric of the cosmos. In the end, the universe doesn't owe us answers. It only offers the stars, the math, and the quiet thrill of the search, and maybe that's enough.